Hello everyone, I'm Jia from Tsinghua University. I'm going to introduce a work on how to bridge the gap between QoE and QoS in congestion control from a large-scale mobile web service perspective. This is a joint work with Meituan and University of Goettingen. Okay, let's get started from the gap between QoE and QoS. Applications value quality of experience, which is QoE. Specifically, for mobile web services, they have no idea what throughput is, but they care about request completion time and image quality. However, congestion control algorithms optimizes the quality of service metrics, which is QoS, describing the transport layer protocol delivery capabilities, which means latency, throughput, loss, or combination of these metrics in different network conditions. Therefore, there exists a mismatch between what congestion control algorithms are optimizing and what applications need. In this paper, we try to give a solution from the perspective of one large-scale mobile web service. We analyze its online user traffic and performance, and then we validate and evaluate our solution based on it. Mobile web service providers focus on the end-to-end performance of each web request. Therefore, we take the request completion time, which is RCT, as QoE, which is the duration from one request started with the user's click behavior to the last associated object is rendered. However, optimizing QoE for CCAs is challenging due to the following reasons. Firstly, the relationship between QoE and QoS is convoluted. QoE metrics are defined for user experience, such as payload time, request completion time, etc. In contrast, QoS metrics focus on the descriptions of transport layer performance, which is not consistent with QoE. For example, for large bulk requests, a reduction in RTT does not imply a QoE improvement, while small request-intensive web pages are not that sensitive to throughput increase. In our emulated experiments, optimal QoE cannot be achieved with lowest RTT, highest throughput, or even optimal QoE oblivious transport layer metrics. In such cases, CCA has no idea what goals the application optimized towards. Secondly, there is a mismatch between the timescale of QoS and QoE. CCAs make decisions from fine-grained QoS information on a short timescale, for example, per packet or per RTT. In contrast, QoE is measured and evaluated at a coarse granularity of the request level, usually around hundreds of milliseconds or even longer, during which the CCAs have already made numerous decisions. So, how should CCAs use sparse QoE information to make their decisions? Our insight in this paper is not to directly optimize the CCA itself, but to introduce a shim layer between the application layer and transport layer to select the appropriate CCA for better QoE. After decades of evolution of CCA, although there may not exist one algorithm to fit all scenarios, we believe that there should always be at least one CCA that behaves well in a certain scenario. So our solution is always use the best one. In this case, we can optimize the real goal of application's QoE. We can also match the timescale of QoE and QoS by selecting CCA. Through QoE-oriented CCA selecting mechanism, we could directly select the appropriate CCA over fluctuating mobile network and application traffic. We therefore introduced Flu to always use the best CCA for the application. Flu network in Harry Potter was a mode of wizarding transportation, which is safe and fast. We hope this also works for the data delivery in mobile web service, safe and fast. However, here comes two key questions when designing a CCA selection framework for large-scale mobile web services. The first one is how to select the best CCA for QoE, which means how to generate the CCA selection policy. While the second one is how to switch between CCAs without traffic interruption. Due to dynamic network conditions, CCA switching may occur during transmission. If we do nothing when switch from CCA1 to CCA2, the traffic has to be interrupted because we need to reset the CCA states. Okay, let's start the design flow from the first question. As we animated earlier, there are many factors that can affect the decision of which CCA to use. Namely, we find that the application requirements and patterns, the fluctuating network conditions, and the empirical CCA characteristics can all contribute to which CCA to use. Therefore, the CCA selection policy takes these three factors as inputs and outputs the best CCA candidates. However, it is not that easy to make the decision, since the inputs are always changing with time and are also not straightforward. We will elaborate this more in the following slides. We'll first take a look at the time variation and complexity of the first two factors, application factor and network factor. Application requirements and patterns include the completion time of a response, the current pending answer size of a response, and the current waiting time for a certain request. These are all changing with the time. The answer size might increase if the application generates more data, and the waiting time monotonically increases with the physical time. This is also true for the network conditions. Here, the network conditions discussed in this paper include bandwidth, packet loss, and the round-trip time. They are changing with the link states, competing flows, and are unpredictable and hard to explicitly know. Therefore, Flu will always keep an eye on what is going on for those application states and network states. Flu monitor both application and network states and pre-process them for later use of CCA selection. As we presented before, we'll first categorize them into application states and network states, and then introduce a monitor to continuously monitor the current values and therefore get a better sense of how is the current application traffic and network condition going. The Flu monitor will also do some pre-processing over the states, such as calculating the statistical value of RTT into minimum RTT variance, and so on. This is for the later use of the CCA selection. According to the features fed by the monitor, selector selects a CCA based on the selection policy, which maps the feature from monitor to appropriate CCA. However, the rich variety of CCAs proposed in recent years each have different scopes of application and different performance preferences. Further, the existing knowledge of the applicable scenarios of CCA is usually empirical. It is very difficult to quantify CCA's preferences over different metrics. Therefore, we utilize a reinforcement learning approach to build a prediction model as a selection policy. We use neural networks to learn the implicit preferences of CCAs. Also, with the help of that end-to-end training towards QoE, an appropriate CCA is selected to directly improve the performance. Well, after selecting the CCA, a second question is how to switch between CCAs without traffic interruption. It is a new question that arises in the CCA selection scenario. Due to the dynamic network, CCAs may switch during transmission, and it is a challenge to switch without performance degradation. Without additional designs, CCA switching may face the following two challenges. Firstly, the new CCA will start at a slow start phase, and the congestion window or send rate increases exponentially from the steady state of the previous CCA until it converges again. The past condition information required for the new CCA still needs time to be collected and estimated. Worse still, since the previous CCA has converged basically, the new CCA's ring convergence will cause a lot of packet loss. Secondly, the network condition observed by the new CCA reflects the condition after the previous one converged. It may not be consistent with the real past condition. For example, if there is already a queue built up in the buffer when switching, the mean RTT observed by COPA will be biased after the switching. In such a case, COPA is unable to make proper decisions to drain the queue. The high RTT may last for tens of seconds, which completely conflicts with COPA's goal of low latency. Therefore, smooth switching is necessary. Ideally, the new CCA should inherit the network path estimation to speed up CCA convergence and avoid performance degradation. Also, it should retain the characteristics of new CCAs consistent with the original design goals. Our first solution is to migrate the face from the original CCA to the one that is going to switch. Face, or sometimes states, is defined by the designers of CCAs to represent different functionalities and behaviors of a CCA. For example, BBR has 4 phases as shown in this figure: startup, dream, probe bandwidth, and probe RTT. We categorize the phases into 2 types: converged phase and non-converged phase. Converged phase means that the CCA has already confidently know about the current path condition and sending traffic. It is usually the phase that a CCA stays most. Non-converged phase is where CCA has not formed a complete awareness of the path or does not fully utilize the available capacity. The non-converged phase includes both the slow start phase and the situation where the CCA would not fill the pipe for other purpose, such as probe RTT in BBR. We adopt different methods to migrate different phases. If the switching happens at the converged phase of the old CCA, Flu makes the new CCA directly enter the converged phase. This avoids massive packet loss caused by the slow start phase after switching. And we do not perform switching as a non-converged phase. But wait, the migration of variables and parameters in CCA is also significant. How should we set them? Therefore, besides the phase migration, we also introduce the variable migration. Variable migration maps variables from the prior CCA to the new one. To ensure the correct mapping of variables between different CCAs, we group all variables into 3 types. Sending rate variables such as congestion window and pacing rate directly determine the sending rate. Observation variables are estimated statistics for the network path. And parameter variables are related to the design of the CCA, which are basically fixed values and will determine the performance. Flu adopts the corresponding migration methods for each type. For sending rate variables, the key issue here is the conversion between the rate-based CCAs and window-based CCAs. The observation variables collected in the converged phase can directly get the new CCA. Flu preserves common features for all CCAs in case some of them are not measured, and Flu does not change parameter variables. Alright, let's put everything together and see how Flu works with a working example. We build the main building blocks of Flu atop Quick in user space, including monitor, selector, and switcher. Flu only requires modification on the sender side. Monitor collects and properties network and application metrics and feeds them to selector. Selector selects the CCA based on the pre-trained selection policy, and switcher then conducts CCA state migration to smoothly switching from the current CCA to the new one. Thus, an accurate and smooth switching of CCA is achieved. We here briefly introduce our experiment results. We implement Flu in Dianping, a popular mobile web service of Meituan company with 10 million daily active users. Our experiments are conducted in production where clients are heterogeneous, including different OS, HTTP versions, etc. We manually enable Flu for 5% of the users for evaluation and collect logs for 4 days, resulting in more than 35 million request logs covering users from more than 50 countries and regions. As a comparison, we set up another 5% of the users to use Cubic, BBR, Copa, Westwood, and Vivace respectively. Okay, let's first take a look at the application performance in the real world. Compared to existing candidates such as Cubic, BBR, and so on, we can clearly see that Flu achieves a QoE improvement of 14% in real scenarios. This demonstrates the effectiveness of always selecting the best CCA. It does help the application to have better QoE results. What's more, such an improvement happens not only for the average values, but for the tail percentiles as well. We also present the other percentiles of the same experiment on the right side. We can see from the red bars that Flu is even able to reduce the 99th percentile of RCT by about 25%. We further analyze the transport layer performance under different scenarios. we consider two performance metrics, smooth RTT and throughput. We put the normalized delay and throughput of flu and different candidates on the figure. The more closing to the down right corner, the better performance a solution is. As we can see that in the cellular scenarios where there is few movement, flu is able to push the optimal frontier of existing baselines forward by achieving better delay and throughput in the same time. We also evaluate flu in another scenario where the network condition can be more fluctuating. Still, flu generally achieves the highest throughput with the lowest latency. The improvement of flu demonstrates that, besides QoE improvements, directly optimizing the application QoE through CCA selection approach can further improve transport layer capabilities. We also evaluate the effectiveness of the state migration mechanism and present the RTT during migration. The reason behind the RTT consistency is the rapid migration of congestion window during the switching. Flu achieves fast and safe congestion window convergence and maintains CCA consistency. For real-world experiments, the average RCT is reduced about 7% with state migration switching. In conclusion, here might be some takeaways from our work. CCAs might be on the Pareto optimal frontier of QoS, but different CCAs wins in different scenarios in terms of QoE. So always selecting the best CCA can improve the QoE for applications. And flu monitors both network and application metrics, selects the best CCA with reinforcement learning, and ensures CCA switching consistency. Large-scale production deployment shows 14 improvement on QoE. Okay, that's all. Thanks for your listening.